Today we're going to discuss inductance of an isolated conductor, and we're going to have two parts to this discussion. Today we're just going to focus on the inductance due to flux which is internal to the conductor. But before we dive into the topic for today, as always, let's do a quick recap of what we saw in the last video, and these are important formulas we're going to be using um, in today's discussion as well. So what we saw, I'll start from the right here because we generally make a progression towards the left, and that's what we did last time. So we started with defining magnetic field as being equal to I over 2 pi r, where I is the current through the conductor and r is the distance from the conductor at which we are measuring our magnetic field. We then moved over to field intensity B, which was equal to mu times h, where mu is the permeability. We then discussed the concept of magnetic flux phi given by BA cos theta, where B is, of course, the field intensity, is the surface area through which the field lines are passing, and theta is the angle which the normal of that surface makes with the field lines. We then moved over to the concept of flux linkages, which was given by n times the flux, where n was the number of turns the conductor made, basically the number of times the current was linking the flux. And we'll get into this discussion a little bit today as well. And we finally found our formulation for the inductance L, which was given by lambda over I, and the unit for that was Henry. So before I dive into these diagrams that I've drawn out here, so that's the other thing you'll notice. I've drawn some figures out here, which I normally don't do because I like to draw them as I'm explaining a concept. But today's discussion for that, this was central, and these were a little bit difficult to draw out here. You see, I've made an attempt to draw something out in a 3D kind of a view, so it makes your understanding a little bit easier. So before I explain what I've done here, let's take a step back and see what we've seen so far. So going back to our solid cylindrical conductor, when we say there's a current I passing through this, what we said was there are flux lines around it, right? And our right hand rule gives us that the flux line in this case would be in a clockwise direction. But not only are there flux lines external to the conductor, there are flux lines internal to the conductor as well. So there'll be flux lines in here as well, and which is what I've drawn out here. In this case, I've imagined the current coming out of the screen, and therefore we have the flux lines going in the counterclockwise direction. And that's going to be our focus today, just the flux lines in here. The other thing I want to bring to your attention is we're talking about an isolated conductor. Now, this is not a practical case because generally you'll always have another conductor that's the return conductor. But what we're imagining here is the return conductor. Is a distance so far away that the current through the return inductor is not affecting the flux of this this conductor, right? And that's just an assumption we're making for now. We're going to get the formulation for the isolated conductor due to internal flux, and then in the next video due to external flux, and then in the videos after that we're going to bring the return conductor into the picture as well and see how that impacts our equations. So now coming to this diagram here. So to calculate the inductance due to all the internal flux, what we're going to do is we're going to take a point that's x distance away from the center. So x is less than r, and then we're going to imagine a surface area ds which has this very small width. So the reason we're saying ds is it's a differential surface, and it has a width of dx and a length of 1 meter, and that's kind of why I wanted to draw this out so it's a little bit clearer to you. Here of course it's exaggerated a little bit, so the distance dx is not really a differential distance. It's pretty large here, and the reason for that is because I wanted you to clearly see what's happening. So if you imagine again this, the flux lines are going in a counterclockwise direction. So if just between x and dx there's a flux line going here which is d phi, and then that's a differential flux going through this differential surface area of width dx and length 1 meter. Now you'll ask why 1 meter? The reason being we're trying to calculate a generic formula, right? We do not know the length of a conductor and we want the equation we get at the end of the day to be applicable for any length of the conductor. So the answer, the formulation we're going to get today is going to be basically L. We're going to get that in terms of Henry per meter. And what that's going to allow us to do is for whatever length of conductor, we can just multiply the formulation we get today and we'll get for that many meters what's the inductance. Now let's come back to this. So at a distance x, what else do we have? At a distance x, there's a current I that's going through the conductor, that's passing through the conductor. But at a distance x, where x is less than r, not all of the current is passing through there. There's only a fraction of the current I that's passing through there, and let's call that current I of x. Now, due to this I of x, there is magnetic field H of x. Okay? Due to this magnetic field, we can calculate the magnetic field intensity B of x. And these are kind of the steps we're going to follow today as well in the derivation, right? So at this point x again, we have a current I of x, which causes a magnetic field H of x, which has a field intensity of B of x. There is a differential flux here because we're only calculating flux through a differential area, right? So we're going to get d phi of x, and then this I of x, there's a flux being linked due to this I of x. That flux linkage is d lambda x. What we're then going to do is, so we'll go through, we'll find out hx, bx, d phi of x, d lambda of x. Now we will then get all our internal flux when we integrate d lambda of x all the way from 0 to r, right? Because x can hold any value between 0 and r. So that's going to be the steps of our derivation. But before we even go into the steps of the derivation, there are some key concepts I want you to understand, because the math of it is very easy, right? You have all these formulas, I've explained the steps, you can just go ahead and plug in the values after that, right? But before we plug in the values, let's see some of the concepts we'll be using to do our math manipulation, right? So let me talk to you about some key points. And these are not always very evident in textbooks and in university lectures. So I'll just quickly talk about them a little bit. The very first one is an assumption we make. So the assumption we make is that the current density J is uniform. Current density, if you remember, we spoke about current density before as well. We said that it's given by the alphabet J, and we're going to assume is constant. Now, if you remember our discussion from skin effect, we know this is not 100% true. Current density is not constant for a AC circuit. There's more current closer to the surface of the conductor. But we can make this assumption because for 50 Hertz or 60 Hertz systems, at those frequencies, this assumption holds true. If you remember from skin effect, the current density that depended on the frequency. So at very high frequencies, yes, you need to take skin effect into consideration. But at lower frequencies of 50 or 60 Hertz, at which most power systems operate irrespective of where you're in the world, you can ignore the effects of skin effect. So for 50 or 60 Hertz, skin effect can be ignored. And therefore we can get away with making that assumption. What does that mean now for our calculations here? Let me go up and see our diagrams here. So at that distance x, what's the current density there? Let me just write that down. So J of x is equal to Ix, the current at that point, over the area. Because we know current density is defined by current over area. So Ix over pi x square. And what's the current density for the whole conductor? That's I over pi r square, because I is the current through the conductor and r is the radius for the conductor. If you're assuming that the current density is the same throughout, so at any point x less than r, the current density is going to be the same as I over pi r square. So what that implies is Ix over pi x square is equal to I over pi r square, and what that gives us is I of x is equal to x over r square times I, and this is going to be our first equation, and we're going to use this down the line. So this is one of the key points I wanted to bring to your attention. So this is one. Okay, now let's go to another key point that's important. Let's discuss number of turns. Remember, this is important for lambda, right? Number of turns n. We saw that we know that lambda is n times phi. So therefore, let's kind of understand this n value a little bit better. If you remember from last time, and I'm going to try to draw this a little bit, and I want you to kind of visualize this in 3D if you can. That's the conductor with 3 turns. It has a current I passing through here. Due to this current, we have flux lines. And what we said here, so let's say there are flux lines, there's a flux line here, right? We said lambda here, because it's going through the surface 3 times, it's cutting the surface thrice, so we said n was 3 in this case. Now what's really happening, it's actually, we can also look at it another way. We can say that the current that's being linked, so the current's passing through here once, twice, thrice, so the current that's being linked, the total current is 3 times the current that's passing through the conductor, right? And in essence, it's n is then the ratio of the current that's being linked to the current that's passing through the conductor. What's happening in our case? In our case, we don't have any turns, but what's the current that's being linked? The current that's being linked is only I of x. At a distance x, for this flux lines, the current that's being linked is I of x. So the number of turns in our case is going to be I of x over I. If you look at equation 1, what is I of x over I? That is equal to x square over r square, and this is going to be our equation 2. So the first thing I want you to remember is the current density is constant. We've made that assumption. The number of turns, we have a formulation for that. Now let's look at another point before we go into our derivation. Mu is important again, right, for us. So we remember mu is given as mu r times mu naught. Now mu r for non-magnetic materials is 1. So most of our materials that make up our conductor are things like aluminum, copper. These are non-magnetic materials. And even if you look up the tables, the values for these, you'll see that mu of r is basically 1. So what that implies is mu is equal to mu naught, which is equal to 4 pi into 10 to the power minus 7. That's the value we get for mu naught in our case, because mu of r for non-magnetic materials like aluminum, copper is equal to 1. So that's the other observation I want you to keep in mind as we do our derivation. The fourth point is, Let me draw that surface out here again. The surface that we're considering, this one. Width dx and length 1 meter, right? That's what we said. So let's draw that out here. So that's your surface area. This is 1 meter. This width is dx. And this is our surface area, ds. We have flux line passing through this, dfi. And what's the normal to this? So normal to this is perpendicular. So what's the angle the normal is making with the flux? So let's write that down here. Theta is equal to 0, which implies cos theta is equal to 1. Also, what's the area? It's dx times 1. Dx times 1 meter, which gives us dx. So I want you to remember this as we do our derivation as well, because this will come in handy where when we said flux phi is equal to BA cos theta. So at that time, now you know your A, you know your cos theta is 1. So this will be helpful when we are writing our formulation down for that. So those are the key points I wanted you to remember. Once again, let's have a look at them very quickly. The first one, current density is assumed to be the same. That gives us Ix, the value for Ix. Then the number of turns, we saw what number of turns really means. It's basically the ratio between the current linked over the total current. So that we have that equation here, Ix over I. We've seen that for our case, mu of r can be assumed to be 1, and therefore mu is nothing but mu naught. We've seen that for the surface area, we've considered what is our area. It's dx, and cos theta in this case is 1. Let's now do our derivations. Once you have this knowledge, the derivation after this is relatively very straightforward. So let's do the derivation. The very first step in the derivation, h of x is equal to I of x over 2 pi x. Let this be equation 3. Now from equations 3 and 1, so what was equation 1? I of x is equal to x square over r square times I. If we substitute that here, what instead of I of x, we're going to get h of x is equal to x times I over 2 pi r square. Then let's look at b of x. We know that that's mu times h of x. We've seen here that mu can be written as mu naught for our case. So let's write that. We have mu naught x I over 2 pi r square. We'll write that down because mu is equal to mu r times mu naught, and mu r is equal to 1. Then we go to calculating our differential flux through our differential surface area. We know that that's given by BA cos theta. In our case, it's BX times DX, which is equal to mu naught x I over 2 pi r square times dx, and this is because area is dx times 1. We've seen that, and also theta is equal to 0, implying cos theta is equal to 1. So we've seen this. Step 4, let's calculate our d lambda x. This will be nothing but n times t phi of x. We know that our n is given by x square over r square. We've seen that up in our key points discussion, times d phi x is this, equation right here. So we can write that as 2 pi r square. I'm just going to bring the x term out here, so it becomes x dx, and I'll write here because n is equal to x square over r square. Let's go to our step 5. We know that the internal flux linkages can be given by integrating this for x between 0 to r. Oops, sorry about that. Let me come down a little bit, make some more space. So you've seen this. Let's do that integral. So that means the flux internal is, so let's take out all the constant values. So mu I 2 pi r to the power 4 now, and then inside the integral we have 0 to r x cube dx, and that gives us a value of that being equal to mu I over 8 pi, because when you do your integral from 0 to r x cube dx, that is equal to r to the power 4 over 4, r to the power 4, and this cancel out, and you have 4 multiplying with 2 pi to give you 8 pi. I'm almost running out of space here, so let's kind of wrap this up. What this means is your flux internal to the conductor is nothing but 1 by 2 times 10 to the power minus 7, and I'll show you why that is, times I, the units are Weber turn per meter. Remember, we are doing this for 1 meter length, so therefore this is per meter. Let me just circle that for you, or rather highlight that for you here, because this is an important formulation we'll carry forward to our discussions in next video. The reason we get this is because mu naught we know is 4 pi times 10 to the power minus 7. So once we substitute mu naught here, we get this value here. And our final step, L internal, is lambda internal over I. Once we use that, I and I get cancelled out, so we have L internal is equal to 1 by 2 times 10 to the power minus 7 Henry per meter, and this is what we wanted to find out. We wanted to find out the inductance due to the flux internal to the conductor. And what's a very important observation we make here, we see that this is a constant. It's independent of the radius of your conductor. So you could have a small conductor in radius, you could have a large conductor in radius. This is independent of that radius. The only thing it depends on is the length. So how long is your conductor under consideration? That's all that matters, right? So that's a key observation. We're going to carry this observation forward into the next video, where we're going to find out the inductance due to external flux, and we're going to sum those up and see the results that we get. All right, till that time, I hope you have a good time. I hope everything was clear today. It improved your understanding a little bit. If you have any questions or comments, please leave them in the comment section below, and I hope to hear from you, and see you in the next video. Take care. Bye now.